Hello and welcome to the YouTube channel D Creations Resources. Today we are going to talk about music. I think in the background you may be able to hear chirping of birds. So that itself is our natural background music for this particular episode. I am Dr. Deepthi Sidhaye and I am going to read out an article I had written in the magazine Book Turn. The title of the article is The Physics of Music, How Sound Becomes Symphony. So let's begin. Have you ever wondered why a sitar sounds different from a harmonium, even if both the musical instruments are playing the same notes? Welcome to the physics of music, where science and arts collide in a beautiful invisible dance of waves and vibrations. Music surrounds us everywhere, from the gentle hum of a violin string to the booming bass of a speaker. But behind every note, rhythm, and harmony lies a fascinating world of physics. Music may feel like pure art, but it is also science in motion. A dance of waves, vibrations, and mathematical patterns that give rise to the music we love. In fact, every sound we hear is a result of simple physical principles. What is sound? At its core, sound is a vibration that travels through a medium, usually air, in the form of waves. When one plucks a sitar string, hits a drum, or sings a note, one creates vibrations in the air. These vibrations travel as waves, with compressions and rarefactions of air molecules. In other words, when you pluck a sitar string, it pushes air particles, creating regions of compression and rarefaction. These pressure variations spread out as waves, eventually reaching our ears. Your ears pick up those waves and translate them into what your brain interprets as sound. So, what are the key properties of a sound wave? Let's see them one by one. Let's begin with frequency, which is measured in hertz. In simple terms, frequency talks about how fast the wave vibrates. This determines the pitch of the sound. High notes have high frequencies, that is treble. Low notes have low frequencies, that is deeper tones or bass. Next is wavelength. Wavelength is the distance between wave peaks. For sound, wavelength is the distance between two places where the air is squeezed the same way in the repeating pattern. When the wavelength is short, the pulses are packed close together. The sound is high-pitched, like a squeaky whistle. This corresponds to high frequency. When the wavelength is long, the pulses are far apart. The sound is low-pitched, like a big drum or a lion's roar. This corresponds to low frequency. So, wavelength and frequency are inversely proportional to each other. Now let's move on to amplitude. Amplitude represents how big the vibrations are. This determines volume or intensity of sound. Larger vibrations sound louder. You can clap very softly or you can clap as loud as you can. The louder clap has a bigger amplitude. Timbre is the next key property, which is the unique quality or character of a sound. You must have noticed that two different musical instruments, for example a flute and a trumpet, sound different even on the same note. The cause is this property of timbre. Let us understand this with an analogy. A red crayon and a blue crayon can both draw a straight line of identical length and thickness, isn't it? But the lines look different because their color is different. Timbre is like the color that leads to differentiation between two musical instruments playing the same note. Actually, every musical instrument is like a physics laboratory. Different designs manipulate sound waves in unique ways, creating the wide palette of timbres we hear. String instruments like guitars and violins rely on string vibrations. The length, the tension, and the thickness of the string all control pitch. Shorter strings produce higher notes, while longer ones generate lower notes. Wind instruments use columns of vibrating air inside pipes. The length of the tube changes the wavelength, which changes the pitch. That's why pressing keys on a flute or saxophone alters the note we hear. You can also open and close the holes on a flute, isn't it? Percussion instruments rely on surface vibrations. A drum's membrane, when struck, vibrates, and its size and its tension determines whether the sound is deep, booming, or it is sharp. When you hear a single musical note, you are actually hearing many frequencies at once. The main frequency is called the fundamental, but layered on top are higher frequencies which are called harmonics or overtones. These harmonics shape the timbre of sound that lets us tell the difference between, say, a guitar and a violin, even if they are playing the same pitch. Without harmonics, all music would sound flat and monotone. So, what does the science of singing look like? Well, your voice works like a musical instrument. When you sing, your vocal cords vibrate to produce sound. Your throat, mouth, and nasal passages shape that sound. Pitch is controlled by the tension in your vocal cords. Tighter cords equal to higher pitch. Volume is controlled by how much air you push through. In order to understand why the music feels so powerful, let us talk about one fundamental principle in the physics of music. It is called resonance. Resonance happens when an object naturally vibrates at certain frequencies and amplifies sounds at those pitches. This is why a singer can shatter a wine glass with just the right note. Here, the sound's frequency matches the glass's natural vibration, and that is why it breaks. In instruments, resonance chambers like a guitar's hollow body or a piano's soundboard amplify the sound, making it rich and powerful. So, by now you must have understood that music is where science meets arts. The physics of music shows us that every note we hear is a part of a larger mathematical dance. It is a story of vibrating molecules, mathematical ratios, and resonant frequencies blending into harmony. But that doesn't take the magic out of it. In fact, it adds to it. Understanding the waves, vibrations, and harmonics behind music helps us appreciate not just the talent of musicians, but also the wonder of the physical world. You can also say that music is physics you can feel in your bones, in your brain, in your soul. Music may stir the soul, but it's grounded in the laws of physics. Understanding the science behind music doesn't take away its magic. It deepens it. The next time you put on your headphones to listen to your favorite song or strum a chord, remember, you're not just enjoying music. You are experiencing both art and science in perfect symphony. Thank you. You were listening to an article on physics of music, how sound becomes symphony. The article is written and read out by Dr. Deepthi Sidhaye and is published in Book Turn. You heard the article on the YouTube channel Decreations Resources, a YouTube channel dedicated to educational resources. Thank you.